Hello students, welcome back to our chemistry class. Let me start with a thought. Have you ever noticed how neatly books are arranged on the shelves of a library? Each row has a purpose, a theme, and a natural order. The periodic table of elements works in a very similar way. In chemistry, these rows are called periods. The modern periodic table has 7 horizontal rows, each called a period, and here's the fascinating part. Every time you move to a new period, you're essentially opening up a brand new electron shell around the atom's nucleus. Isn't it amazing that something so microscopic follows such a clear and predictable order? For example, hydrogen with atomic number 1 has just one shell, so it lies in the first period, while sodium, atomic number 11, has 3 shells and therefore sits in the third period. Now let's dig a little deeper. The number of the period tells us exactly how many electron shells are occupied in that element. Period 1 is the simplest. Hydrogen and helium have just one shell, the K shell. Move to period 2, and suddenly, the elements from lithium to neon have 2 shells, the K and L shells. Period 3 is larger still, where sodium to argon occupy 3 shells, K, L, and M. So, the period number is like a direct mirror of the number of electron shells. And this elegant relationship is what makes the periodic table a living map of recurring chemical properties. This repetition of behavior, once every new shell is filled, is what we call periodicity. The first 3 periods show us a neat pattern. Period 1 is the shortest. It has only 2 elements, hydrogen and helium. Period 2 has 8 elements, from lithium to neon. Period 3 also has 8 elements, from sodium to argon. That means in the first 3 rows alone, we already cover 18 elements. What's more exciting is that these short periods already reflect the law of periodicity. For example, lithium, sodium, and potassium, though in different periods, all show similar chemical behavior because they start their respective rows with a single electron in the outermost shell. Let's zoom into period 2. It starts with lithium, atomic number 3, whose configuration is 1s2, 2s1. Then comes beryllium, 2s2, and it continues until neon, which ends with a full 2p6 configuration. As you move from left to right, the atomic numbers go from 3 to 10, and the properties shift. Lithium and beryllium are metals, boron is a metalloid, and carbon, nitrogen, oxygen, and fluorine are nonmetals. Finally, neon is a noble gas with a complete octet and valency 0. Across this single row, we see the full journey from reactive metals to inert gases. Now let's look at period 3. It begins with sodium, atomic number 11, configuration 2, 8, 1. Magnesium follows with 2, 8, 2. As we move across, we see aluminium, silicon, phosphorus, sulfur, chlorine, and finally argon at atomic number 18 with a configuration of 2, 8, 8. The valency changes regularly across the period, starting with +1 for sodium, +2 for magnesium, +3 for aluminium, then reaching 0 for argon. Metallic character decreases from sodium to aluminium, silicon acts as a metalloid, and elements like sulfur and chlorine are strongly nonmetallic. This period perfectly demonstrates the smooth transition from metal to metalloid to nonmetal to noble gas. But why do properties change so predictably across periods? The answer lies in the nucleus. Across a period, the number of protons increases, pulling the electrons closer to the nucleus. This makes the atomic radius shrink. As a result, it becomes harder to remove an electron, so ionization potential increases. Similarly, the electron affinity and electronegativity also rise because atoms want to complete their octets. Meanwhile, metallic character decreases while nonmetallic character strengthens. For instance, sodium on the left is a soft metal, while chlorine on the right is a strong nonmetal. These trends show how the repetition of valence shell patterns drives periodicity. So let's wrap it up. Periods are the 7 horizontal rows of the periodic table. The number of the period tells us how many electron shells the atoms of its elements have. The first 3 periods contain 18 elements, and even in these, we see periodic trends. Across a period, atomic size decreases, ionization energy increases, and the nature of elements shifts from metallic to nonmetallic, ending with noble gases. This is the beauty of the periodic table. It's not just a chart of symbols, but a roadmap of recurring chemical behavior. I hope this session has helped you see how periods are the key to understanding chemical patterns. In our next class, we'll explore groups in the periodic table, which reveal another dimension of periodicity.